2 degrees. It sounds almost harmless, the difference between a cool morning and a slightly warmer one. You'd barely notice it stepping outside. But when we're talking about the average temperature of an entire planet, 2 degrees Celsius isn't a minor inconvenience. It's the difference between a world we recognize and one we don't. Scientists have been warning about this threshold for decades. World leaders signed agreements trying to prevent it, and yet, right now, we are on track to cross it. What happens when Earth's global average temperature climbs 2 degrees above pre-industrial levels? The ice sheets begin their final retreat, the oceans rise and acidify, entire ecosystems collapse. Weather systems that have been stable for thousands of years go haywire, and hundreds of millions of people face a future of drought, flood, famine, and displacement. This is the story of 2 degrees and why that tiny number carries the weight of civilization itself. To understand why 2 degrees Celsius has become the defining threshold of our era, we need to step back and understand what global average temperature actually means and why a seemingly small change in that number can have consequences that dwarf anything in recorded human history. The Earth's average surface temperature is not a number you can measure at any single location. It's a statistical construct, an average of thousands of measurements taken across land surfaces, ocean surfaces, and the lower atmosphere, integrated over time. Right now, Earth's global average temperature is approximately 1.2 degrees Celsius above the pre-industrial baseline, which scientists typically define as the average temperature between 1,850 and 1,900 before large-scale industrial activity began significantly altering atmospheric composition. That 1.2 degrees of warming we've already experienced. It has already caused measurable, significant changes. Glaciers are retreating worldwide. Arctic sea ice extent has declined dramatically. Sea levels have risen. Extreme weather events have become more frequent and intense. Coral reefs have experienced widespread bleaching. The changes are accelerating, and we're only at 1.2 degrees. The 2-degree threshold has its origins in scientific research from the 1970s and 1980s, when climatologists began trying to identify at what level of warming the impacts would transition from serious to potentially catastrophic for human civilization and Earth's ecosystems. The number 2 degrees Celsius emerged from these analyses as a rough boundary, not a cliff edge, where everything is fine on one side and catastrophic on the other, but a zone where risks escalate dramatically, where feedback loops may strengthen and accelerate warming, and where many of the changes become effectively irreversible on human timescales. The 2015 Paris Agreement codified this scientific consensus into international policy. Under the agreement, nations committed to limiting warming to well below 2 degrees Celsius above pre-industrial levels, with efforts to limit warming to 1.5 degrees. These numbers weren't chosen arbitrarily. They represented the range within which scientists believed the worst-case scenarios could still be avoided. But understanding these numbers requires understanding something subtle about how climate works. The difference between a climate that is warming and a climate that has warmed. When we say the planet is 1.2 degrees warmer than pre-industrial times, we mean the average has shifted. But that average shift is not uniform. Some places have warmed much more. The Arctic has warmed nearly 4 times faster than the global average. Some seasons have changed more than others. The warming isn't a blanket of uniform heat spread evenly over the planet. It's a disruption to the complex, interconnected system of heat distribution that has maintained Earth's climatic patterns for thousands of years. Climate is not just temperature. It is the sum of all the ways the planet moves heat around. Ocean currents that carry warm water to cold regions, atmospheric circulation patterns that drive wind and precipitation, the reflectivity of ice and snow that bounces sunlight back into space, the capacity of forests and oceans to absorb and release carbon. When you add energy to this system, which is what greenhouse gases do, by trapping heat that would otherwise escape to space, you don't simply raise temperatures uniformly. You disturb the entire circulation system. 2 degrees of average global warming means somewhere between 4 and 6 degrees of warming at the Arctic poles, significant warming of ocean surfaces worldwide, intensification of the hydrological cycle as more water evaporates from warmer surfaces, disruption of established weather patterns, and acceleration of processes like ice sheet melt that will continue driving changes for centuries even after temperatures stabilize. The 2-degree world is not a version of today's world that's slightly warmer. It is a fundamentally different planetary state, with different geography, different ecosystems, different ocean chemistry, different weather patterns, and profoundly different prospects for human civilization. This chapter is just the beginning of understanding what that means. Let's start building the picture. Nothing captures the consequences of a 2-degree world more dramatically than what happens to the planet's great ice sheets. These massive accumulations of frozen water, the Greenland ice sheet in the northern hemisphere and the Antarctic ice sheet in the south, contain enough water to raise global sea levels by more than 200 feet if they melted entirely. Understanding what 2 degrees means for these ice giants is essential to understanding the future of every coastal civilization on Earth. Let's start with Greenland. The Greenland ice sheet covers about 660,000 square miles, roughly 3 times the area of Texas, and contains enough ice to raise global sea levels by about 24 feet if it melted completely. Currently, Greenland is losing ice at an accelerating rate. Satellite measurements show the island losing hundreds of billions of tons of ice per year, a rate that has roughly quadrupled since the 1990s. A 2-degree world would be devastating for Greenland in a specific and alarming way. It likely crosses what scientists call a tipping point, a threshold beyond which the ice sheet's decline becomes self-sustaining and irreversible on any meaningful human timescale. Here's the mechanism. As the ice sheet melts, its surface elevation decreases. Lower elevations experience warmer temperatures, temperature drops with altitude, so the reverse is also true. As the ice surface descends, it enters warmer air, melting faster. As it melts faster, it descends more. The process feeds back on itself in a vicious cycle. Multiple research groups have identified the threshold for this irreversible decline somewhere between 1.5 and 2 degrees of global warming. A 2023 study published in the journal Nature Climate Change concluded that the Greenland ice sheet may already be destabilizing, with the current 1.2 degrees of warming sufficient to eventually cause significant sea level rise regardless of future emissions. At 2 degrees, the fate of the Greenland ice sheet appears to be sealed, not immediate collapse, but a commitment to centuries of ongoing melt that could ultimately contribute 20 or more feet to global sea level. Antarctica is more complex because it consists of 3 distinct regions with different characteristics. The East Antarctic ice sheet is the largest and, by current analysis, the most stable, though even here, some outlying glaciers are showing acceleration. The West Antarctic ice sheet is fundamentally different. It's a marine ice sheet, meaning large portions of it rest on bedrock that lies below sea level. This makes it vulnerable to a process called marine ice sheet instability. As the ocean warms even slightly, it eats away at the ice at the grounding line, the point where the ice sheet lifts off the bedrock and begins to float. As this grounding line retreats, more ice is exposed to the relatively warm ocean, melting faster and causing the grounding line to retreat further. Like Greenland's altitude-driven feedback, this is a self-amplifying process. Several West Antarctic glaciers, including the Thwaites Glacier, nicknamed the Doomsday Glacier, are already showing signs of this instability. Thwaites is particularly alarming. It's roughly the size of Florida and contains enough ice to raise global sea levels by about 2 feet on its own. But more critically, it acts as a buttress for the broader West Antarctic ice sheet. If Thwaites loses its stabilizing role, it could unlock a larger collapse that contributes much more to sea level rise. Recent research suggests that Thwaites may already be past its tipping point, though the timeline for significant change spans decades to centuries. Then there are the ice shelves, the floating extensions of the ice sheet that jut out over the ocean. Ice shelves don't contribute directly to sea level rise when they melt because they're already floating, but they act as brakes for the glaciers behind them. When an ice shelf collapses, the glacier it was restraining can accelerate dramatically. We've already seen this with the Larsen B ice shelf, which collapsed spectacularly in 2002, and the glaciers behind it accelerated eightfold within months. At 2 degrees of global warming, the remaining ice shelves face dramatically increased risk of collapse. Atmospheric warming melts the upper surface, creating meltwater ponds that drain into crevasses and fracture the shelf. Ocean warming attacks from below. The combination makes ice shelf survival increasingly precarious. What does all this mean for sea levels? In a 2-degree world, the best scientific estimates suggest we're looking at roughly 1 to 2 feet of sea level rise by 2100. Potentially more if ice dynamics accelerate beyond current models. But critically, this rise doesn't stop in 2100. The climate system has enormous inertia. Committed warming and committed sea level rise will continue for centuries, even after temperatures stabilize. Some models suggest that the long-term sea level rise commitment from a 2-degree world could be 10 feet or more over the coming centuries. 1 to 2 feet of sea level rise might not sound catastrophic, but combined with the storm surges from increasingly intense hurricanes and typhoons, it's enough to make coastal flooding events that currently happen once in a century occur annually. Cities like Miami, New Orleans, Bangkok, Amsterdam, and Mumbai face dramatically increasing flood risks. Low-lying island nations, the Marshall Islands, Tuvalu, Kiribati, may become largely uninhabitable. And we're only talking about 2 degrees. The ice sheets don't care about political agreements or economic costs. They respond to temperature, and the temperature is rising. The ocean covers 71% of Earth's surface. It has absorbed more than 90% of the excess heat trapped by greenhouse gases since the Industrial Revolution. It has absorbed roughly 30% of the carbon dioxide emitted by human activities. In doing so, it has protected the atmosphere from warming even faster than it otherwise would have. But this service to the climate has come at a devastating cost to the ocean itself. And in a 2-degree world, the ocean's condition deteriorates dramatically. Let's start with temperature. The ocean is not a single uniform body of water. It has layers: the warm surface layer that interacts with the atmosphere, deeper intermediate layers, and the cold, deep ocean that moves on timescales of centuries. These layers interact through a complex system of overturning circulation, the global conveyor belt of ocean currents that distributes heat around the planet. As the surface ocean warms, the temperature difference between warm surface waters and cooler deep waters decreases. This reduces the density gradient that drives circulation, potentially weakening or disrupting the overturning. The most consequential example is the Atlantic Meridional Overturning Circulation, or AMOC, the system of currents that includes the Gulf Stream and which is responsible for keeping Western Europe several degrees warmer than it would otherwise be at its latitude. AMOC has already slowed by approximately 15% since the mid-23rd century, according to paleoclimate reconstructions. In a 2-degree world, it could slow significantly further. A substantial weakening of AMOC would have paradoxical effects. While the rest of the world warms, Western Europe could actually experience cooling with more severe winters and disrupted agricultural seasons. Meanwhile, the eastern coast of North America would see accelerated sea level rise as the Gulf Stream's northward push of water weakens. The threat of a complete AMOC shutdown, an event that has occurred during past ice ages, is one of the most feared climate tipping points. While most scientists consider a full shutdown unlikely at 2 degrees, the probability is not zero, and the consequences would be severe. Drastically altered weather patterns across the entire North Atlantic region, with effects rippling globally. Ocean warming has a direct and immediate impact on marine ecosystems, and nowhere is this more visible than in coral reefs. Corals are extraordinary organisms that build their calcium carbonate skeletons in intimate partnership with photosynthetic algae called zooxanthellae. The algae live inside coral tissue and provide up to 90% of the coral's energy through photosynthesis. But this relationship is temperature sensitive. When water temperatures rise even slightly above the coral's optimal range by 1 or 2 degrees Celsius for an extended period, the coral expels its algae in a stress response. The coral turns white, bleaching. Without its algae, the coral receives no photosynthetic energy. If the bleaching lasts long enough, the coral starves and dies. We have already seen massive bleaching events in the 2010s, including an event in 2016 and 2017 that killed roughly half of the Great Barrier Reef's shallow water corals. These events occurred at approximately 1 to 1.2 degrees of global warming. At 2 degrees, research suggests that essentially all of the world's coral reef systems that support about 25% of all marine species and provide food and income for roughly 1 billion people would experience annual or biennial bleaching events severe enough to prevent recovery. Coral reefs as functioning ecosystems would largely cease to exist. The cascading effects on marine biodiversity, fisheries, coastal protection, and human livelihoods would be profound. Then there is the second crisis the ocean faces: acidification. When carbon dioxide dissolves in seawater, it forms carbonic acid. This acid dissociates and releases hydrogen ions, lowering the ocean's pH, making it more acidic. Since pre-industrial times, ocean pH has dropped by approximately 0.1 units on the logarithmic pH scale, representing a roughly 26% increase in hydrogen ion concentration. At 2 degrees of global warming, which corresponds to significantly higher atmospheric carbon dioxide concentrations than today, ocean acidification would continue to worsen. The pH changes might seem small, but they have enormous biological consequences. Many marine organisms, corals, oysters, clams, sea urchins, some plankton species build their shells and skeletons from calcium carbonate, which dissolves in acidic water. As acidity increases, these organisms struggle to build their structures, grow more slowly, and eventually become unable to maintain their shells or skeletons at all. The organisms most at risk from acidification include pteropods, tiny sea snails that form a critical link in the food chain of the Southern Ocean and parts of the Arctic. Studies have already documented pteropods with dissolving shells in waters off Antarctica and the Pacific Northwest. In a 2-degree world, vast areas of the high-latitude ocean may become corrosive to calcium carbonate, fundamentally disrupting food webs that support fish, seabirds, and marine mammals. The combination of warming, acidification, and ocean circulation changes creates a multi-front assault on marine ecosystems that have evolved over millions of years for conditions quite different from what they're rapidly experiencing. Marine species can adapt, but evolution works on timescales of thousands to millions of years. The changes we're imposing on the ocean are happening over decades far faster than evolution can respond. When we talk about climate change, we're not just talking about gradual warming. We're talking about the energization of the Earth's weather system, the injection of more heat energy into the atmospheric engine that drives our weather. And in a 2-degree world, that engine runs harder, faster, and more destructively than anything humanity has experienced in its recorded history. Let's start with the most basic principle. A warmer atmosphere holds more water vapor. For every degree Celsius of warming, the atmosphere can hold roughly 7% more moisture. This extra moisture has 2 profound effects on weather. It intensifies precipitation events when storms do occur, and it intensifies droughts when the atmosphere stays dry by drawing more moisture out of the soil. This seems paradoxical, more rain and more drought simultaneously, but it makes sense when you understand the regional and temporal distribution. In a warmer world, wet areas tend to get wetter, dry areas tend to get drier, and the contrast between wet events and dry events becomes more extreme. We already see this pattern in the climate data. One region experiencing its worst drought in recorded history, while another region deals with its worst flooding, often in the same season. At 2 degrees of global warming, precipitation patterns shift significantly. The monsoon systems that deliver water to billions of people in South and Southeast Asia become more intense and less predictable. The jet stream, the high-altitude wind belt that steers weather systems across North America and Europe weakens and becomes more wavy, causing weather patterns to get stuck in place for longer periods. A storm system that might have passed through in a few days instead stalls for weeks, dumping unprecedented rainfall or maintaining a heat dome over a region. Heat waves deserve special attention because they are perhaps the most direct and immediate manifestation of climate change. In a 2-degree world, events that are currently considered extreme heat events, occurring once every 50 years, would occur approximately 4 to 5 times per decade. Heat events that are currently essentially unprecedented would occur every 5 to 10 years. What does this mean in human terms? The 2003 European heatwave killed approximately 70,000 people. The 2010 Russian heatwave killed approximately 56,000 people and triggered massive wildfires that blanketed Moscow in smoke. The 2021 Pacific Northwest heat dome killed hundreds of people in Oregon, Washington, and British Columbia, a region not accustomed to or prepared for extreme heat. These events, which occurred at roughly 1 to 1.2 degrees of global warming, would be considered relatively ordinary in a 2-degree world. Cities are particularly vulnerable to heat for a reason beyond the obvious: the urban heat island effect. Cities are already warmer than surrounding rural areas due to the heat-absorbing properties of concrete and asphalt, the waste heat from buildings and vehicles, and the lack of evaporative cooling from vegetation. A 2-degree global average warming translates to 3 or more degrees in urban cores. City dwellers, who will constitute the majority of humanity by mid-century, face a disproportionate burden. Tropical cyclones, hurricanes, and typhoons respond to warming ocean temperatures in ways that have been extensively studied. The thermodynamic energy that powers a hurricane comes from warm ocean surface water. As ocean temperatures rise, hurricanes intensify faster, reach higher maximum intensities, and maintain their strength further from the tropics than they historically have. We've already seen this. Hurricane Harvey in 2017, which dumped over 60 inches of rain on the Houston area, was dramatically intensified by Gulf of Mexico waters that were 2 to 3 degrees warmer than the historical average. At 2 degrees of global warming, the frequency of the highest intensity hurricanes, Category 4 and 5, is expected to increase significantly. The rainfall rates of the most intense storms could increase by up to 30%. And as sea levels rise, the storm surges these hurricanes push ashore, reach further inland, and cause more damage than they would with today's sea levels. Wildfire is another domain where 2 degrees of warming has catastrophic implications. The conditions that favor wildfire, hot, dry weather, dry vegetation, and strong winds all intensify in a warmer world. We have already watched this play out. The 2019 to 2020 Australian bushfire season, the 2020 California fire season that burned more than 4 million acres, the 2023 Canadian wildfires that were so extensive they degraded air quality as far south as the Midwestern United States. At 2 degrees, fire-prone regions experience longer fire seasons, more frequent ignition conditions, and larger, more intense fires than any in historical memory. The fire regime in the American West, Mediterranean Europe, Australia, and parts of South America would be fundamentally transformed. Forests that evolved over millennia would be replaced by fire-adapted scrublands, or, in some cases, by bare, eroded hillsides. The economic costs of these intensified weather extremes are already enormous and would grow dramatically in a 2-degree world. Insurance companies are pulling out of high-risk markets. Infrastructure designed for historical climate is increasingly mismatched to the climate it actually experiences. The cost of adaptation, building seawalls, hardening infrastructure, developing heat-resilient agriculture, managing wildfire runs into the trillions of dollars, and some of the most severe impacts may simply not be adaptable at any cost. Perhaps the most frightening aspect of a 2-degree world is not any specific impact, but the possibility that warming of this magnitude could trigger tipping points, thresholds, in the climate system beyond which change becomes self-sustaining and impossible to stop by reducing emissions. A tipping point in the climate system is a threshold condition beyond which the system shifts to a qualitatively different state that it tends to maintain itself, regardless of the initial trigger. Think of it like a ball balanced on a hilltop. A small push sends it irreversibly rolling down. The ball's subsequent motion is no longer determined by the push, it's determined by the slope it's rolling down. The initial trigger becomes irrelevant to the ultimate outcome. Scientists have identified a number of potential climate tipping points. Several of them may be activated at or near 2 degrees of global warming. And the particularly alarming finding from recent research is that these tipping points don't operate in isolation. They can trigger each other in what researchers call a tipping cascade. We've already discussed the Greenland and West Antarctic ice sheet tipping points and the AMOC weakening. Let's explore some additional critical thresholds. The Amazon rainforest represents one of Earth's most critical climate regulators. The Amazon creates its own rainfall through a process called biotic pumping. The vast forest transpires enormous quantities of water vapor that condense and fall as rain, which feeds the forest, which transpires more water. The Amazon is literally making its own weather. This self-sustaining moisture cycle is what allows the rainforest to maintain itself in what would otherwise be a much drier climate. But this system requires the forest to remain largely intact. When deforestation removes trees, the moisture cycle weakens. Less transpiration means less rainfall, which stresses the remaining trees, causing more die-off, which further reduces transpiration. The forest can transition from tropical rainforest to a drier, more open savanna state, a transition that would release enormous quantities of stored carbon into the atmosphere, accelerating warming further. At 2 degrees of global warming, combined with the continued deforestation that has already removed roughly 20% of the original Amazon, researchers estimate that significant portions of the Amazon could be approaching a tipping point. A 2018 study in Science suggested that somewhere between 20 and 25% deforestation could trigger a dieback of the remaining forest, independent of further climate changes. With climate change adding additional stress through drought and heat, this threshold may be lower. A forest collapse in the Amazon wouldn't just release carbon, it would eliminate a biodiversity reservoir containing roughly 10% of all species on Earth, eliminate the rainfall recycling that supports agriculture across South America, and transform the regional climate of an entire continent. Then there is permafrost. Across Alaska, Canada, Siberia, and other high-latitude regions, roughly 1.5 trillion tons of organic carbon are stored in permanently frozen soil. This permafrost has been frozen since the last ice age, preserving organic material from ancient plants and animals that never fully decomposed. As the climate warms, the permafrost thaws. The organic material begins to decompose. Microbes consume it and release carbon dioxide and methane, both greenhouse gases, into the atmosphere. This permafrost feedback is one of the most extensively modeled and discussed amplifying feedbacks in climate science. In a 2-degree world, permafrost thaw releases additional greenhouse gases that further warm the climate, which causes more permafrost to thaw. At some point, this feedback becomes self-sustaining regardless of what humans do with emissions. Some researchers estimate that permafrost carbon emissions could add the equivalent of several additional years of current global emissions to the atmosphere over the coming centuries. Methane hydrates frozen deposits of methane trapped in ice-like structures on the seafloor, and in some permafrost represent another potential carbon feedback. These deposits hold vast quantities of methane, a greenhouse gas roughly 80 times more potent than carbon dioxide over a 20-year period. If ocean warming destabilizes the seafloor hydrates, or if permafrost warming destabilizes terrestrial hydrates, sudden methane releases could cause rapid and dramatic warming spikes. The boreal forests of Canada, Russia, and Scandinavia represent another potential tipping element. These forests, which cover roughly 11% of Earth's land surface, are experiencing warming at roughly twice the global average rate. The combination of warming, drying, increased pest outbreaks, bark beetles thrive in warmer winters, and increased fire is causing unprecedented stress. If the boreal forest transitions from net carbon sink to net carbon source, which some researchers believe may already be happening in parts of the Canadian boreal, this represents yet another feedback amplifying warming. What makes the tipping point question so alarming in the context of 2 degrees is research suggesting that multiple tipping points are clustered in the range of 1 to 3 degrees of global warming. A landmark 2018 paper in the Proceedings of the National Academy of Sciences, led by researchers including Johan Rockström and Will Stephan, warned of a hothouse Earth pathway in which triggering just a handful of these tipping points could put the climate system on a self-reinforcing trajectory toward much higher temperatures, possibly 4 or 5 degrees regardless of subsequent human action. This doesn't mean 2 degrees of warming inevitably triggers a catastrophic cascade. The probabilities are uncertain, and different tipping elements have different threshold temperatures and different relationships to each other. But it does mean that the 2-degree target isn't just about the direct impacts of 2 degrees. It's about whether we can avoid the risk of activating a chain reaction that takes the climate system out of human hands entirely. Earth is currently experiencing what scientists call the 6th mass extinction, a loss of biodiversity at rates comparable to the 5 previous mass extinction events in Earth's geological history. Climate change is one of several drivers of this extinction, along with habitat destruction, pollution, invasive species, and overexploitation. But at 2 degrees of global warming, climate change becomes the dominant driver, and the pace of biodiversity loss accelerates dramatically. Understanding why requires understanding how species relate to climate. Every species exists within a range of environmental conditions. It can tolerate temperature ranges, precipitation ranges, seasonal patterns. When conditions change, species have 3 options. They can move to track suitable conditions, range shifting. They can adapt genetically to the new conditions, evolutionary response, or they can go extinct. Range shifting is happening right now. Species worldwide are moving poleward and to higher elevations as temperatures rise. In marine environments, fish populations are shifting their ranges, with profound consequences for the fishing industries that depend on them. On land, the ranges of many species have shifted northward or to higher elevations over the past several decades. But range shifting is not always possible. Many species require specific habitat types, old-growth forests, particular soil conditions, specific plant communities that don't simply move as temperatures change. Polar species like polar bears, Arctic foxes, and ice-dependent seabirds have nowhere colder to go. Mountain species face the same problem. As they're pushed higher to find cool temperatures, they eventually run out of mountain. Additionally, species don't live in isolation. They exist in complex ecological communities with intricate dependencies, predator-prey relationships, pollinator-plant relationships, parasite-host relationships, Competitive dynamics. When climate change causes one species to shift its range or change its seasonal timing, all the species that depend on it are affected. This is the problem of ecological mismatch. A classic example is the timing of peak insect abundance and the breeding season of migratory birds. In many temperate regions, insect abundance peaks at a particular time of spring that historically coincided with the period when migratory birds were raising their nestlings, the time of greatest food demand. But insect activity is responding to temperature, and bird migration is responding to day length. As spring temperatures advance earlier, insects peak earlier, but many bird species haven't shifted their migration timing sufficiently. The result is a mismatch. Birds arrive expecting a food bonanza, but peak insect abundance has already passed. This kind of mismatch is occurring across many ecological systems and will intensify in a 2-degree world. The intricate temporal choreography that ecosystems have developed over millennia is being disrupted in ways that cascade through entire food webs. Research on the relationship between global temperature and extinction rates suggests that, at 2 degrees of warming, roughly 8% of all species would face high extinction risk from climate change alone. This is approximately 500,000 species, a number comparable to some of the major mass extinction events in Earth's geological history, albeit on a slower timescale. Some ecosystems are more vulnerable than others. Beyond coral reefs, which we've already discussed, Arctic and alpine ecosystems face particularly severe disruption. Mediterranean climate ecosystems, which occur in only 5 regions of the world, the Mediterranean Basin, California, central Chile, the Cape region of South Africa, and southwestern Australia, but contain a disproportionately high share of global plant diversity, are highly vulnerable to increased fire frequency and changing precipitation patterns. Freshwater ecosystems, rivers, lakes, and wetlands are among the most threatened. Many freshwater fish species have narrow temperature tolerances. As rivers warm, cold water species like salmon and trout are pushed to higher elevations. Combined with changes in river flow regimes, less snow, more rain, more intense flooding, lower summer base flows, freshwater biodiversity faces a severe crisis in a 2-degree world. Forests, beyond the Amazon and boreal systems already discussed, face multiple simultaneous stresses. Drought stress directly damages trees and makes them more susceptible to pests and pathogens. Bark beetle outbreaks, which require warm winters to survive, have already killed billions of trees across western North America. In a 2-degree world, these outbreaks intensify and expand to new regions. Forest fire removes additional forest area. The combination could transform the character of forests across large regions, with profound consequences for carbon storage, water regulation, biodiversity, and the livelihoods of communities that depend on forests. There is a profound and disturbing irony in the biodiversity crisis. We don't know what we're losing. The vast majority of Earth's species have never been formally described by science. We're eliminating species whose biology, chemistry, and ecological roles are completely unknown to us. Some of those species might have contained compounds with medical applications. Some might play ecological roles that we don't understand until they're gone. The extinction crisis is a deletion of the book of life, destroying information that evolution accumulated over hundreds of millions of years before we've even had a chance to read it. We've explored what 2 degrees of warming means for the physical and biological systems of the Earth. Now let's turn to the system that faces perhaps the most immediate and certain consequences: human civilization. Roughly 8 billion people depend on a climate that has been remarkably stable for the 10,000 years since the end of the last ice age, the entire span of human civilization. Agriculture, water infrastructure, coastal cities, disease ecology, and virtually every other aspect of how we live have been optimized for the climatic conditions of the Holocene. A 2-degree world represents a departure from those conditions that is unprecedented in the history of organized human society. Start with food. Agriculture is the foundation of civilization, and agriculture is exquisitely sensitive to climate. The major grain crops that feed humanity, wheat, rice, and corn, have optimal growing temperature ranges that have been fine-tuned through thousands of years of agricultural practice and, more recently, through modern plant breeding. For most of these crops, yields decline significantly above certain temperature thresholds during critical growth stages. Research projections for a 2-degree world suggest that wheat yields could decline by roughly 6% globally, with much larger regional declines in already hot regions. Corn yields could decline by nearly 8%. Rice yields could decline by 3 to 7%, with particular impacts in tropical regions where rice is a dietary staple for hundreds of millions of people. These declines occur against a backdrop of a growing global population that is expected to reach nearly 10 billion by mid-century. The geography of food production would shift dramatically. Higher latitude regions, parts of Canada, Russia, and Scandinavia might see some expansion of agricultural potential as growing seasons lengthen, but these regions often have thinner soils, shorter growing seasons, and less agricultural infrastructure than the temperate breadbaskets they would partially replace. The transition would be slow, costly, and incomplete. Meanwhile, agricultural regions in South Asia, Sub-Saharan Africa, and Central America regions that already struggle with food security face the most severe impacts. Higher temperatures, more erratic rainfall, and more frequent drought create conditions for crop failures that could trigger humanitarian crises at unprecedented scale. The global food system, which has become deeply interconnected and interdependent, is also more vulnerable to multiple simultaneous regional shocks than historically fragmented food systems were. Water security is intimately connected to food security and represents one of the most critical human challenges of a 2-degree world. Freshwater availability for agriculture, drinking, and industry is largely determined by the balance between precipitation, evaporation, and river flows. In a warmer world, this balance shifts in ways that disadvantage billions of people. The great rivers of Asia, the Ganges, Brahmaputra, Yangtze, Yellow River, Mekong, and others, are fed largely by glaciers and snowmelt in the Himalayas and Tibetan Plateau. These rivers provide water for agriculture, industry, and drinking to more than 1 billion people across China, India, Bangladesh, Pakistan, and Southeast Asia. In a 2-degree world, the glaciers that feed these rivers continue to retreat. In the near term, this actually increases river flow as more ice melts. But in the longer term, likely within this century, the ice reservoir that buffers seasonal flow depletes and summer river flows decline dramatically. The billions of people who depend on these rivers face a permanent reduction in water availability. Similar dynamics play out in the Andes of South America, where tropical glaciers feed rivers that supply Lima, La Paz, and many agricultural regions. The western United States faces its own water crisis as the snowpack that stores winter precipitation and releases it gradually through summer, Essentially, a giant natural reservoir declines under warming conditions. Human health is another domain severely affected by 2 degrees of warming. The direct health impacts of heat exposure, heat stress, heat stroke, cardiovascular strain intensify significantly. Workers in outdoor occupations in tropical regions already face dangerous heat conditions during parts of the year. At 2 degrees, the window of safe outdoor work in many tropical and subtropical regions shrinks dramatically, affecting agricultural productivity, construction, and other physically demanding industries. Vector-borne diseases, illnesses transmitted by insects and other vectors, expand their ranges as the climate warms. Malaria, dengue fever, Zika virus, West Nile virus, and tick-borne diseases like Lyme disease all shift their geographic distributions in a warmer world. Mosquitoes that transmit these diseases thrive in warm, wet conditions, and their range expansion means that populations with no historical exposure and therefore no acquired immunity face new disease threats. Regions of Europe and North America that currently experience little mosquito-borne disease would face increased risk in a 2-degree world. Air quality deteriorates in a 2-degree world for multiple reasons. Increased wildfire smoke, higher concentrations of ground-level ozone, which forms more readily in heat, and longer and more intense pollen seasons as vegetation responds to warmer conditions. People with respiratory conditions like asthma face worsening health outcomes. The issue of climate displacement, people forced from their homes by climate change impacts, may be one of the defining humanitarian challenges of the coming decades. Rising seas, increased flooding, more intense storms, worsening drought, and declining agricultural productivity all contribute to conditions that make certain regions difficult or impossible to inhabit. Current estimates of climate displacement are necessarily uncertain, but multiple analyses suggest that in a 2-degree world, hundreds of millions of people could be driven from their homes or their home regions by climate impacts over the course of this century. Some will move from rural to urban areas within their countries. Some will cross international borders. The geopolitical consequences strain on receiving countries, potential conflict over resources, destabilization of governments in the hardest-hit regions add a layer of political risk to the already severe human costs. 2/3 of the world's cities, with populations over 5 million, are located in coastal or low-lying areas. These urban centers, home to hundreds of millions of people and representing trillions of dollars of infrastructure and economic activity, sit directly in the path of the 2 most severe direct physical impacts of climate change, rising seas, and intensifying storms. Miami is often cited as the most vulnerable major city in the United States to sea level rise. It sits on a foundation of porous limestone, which means traditional flood defenses like seawalls have limited effectiveness. Water seeps up through the ground, even when it can't come over the top. The city's streets already flood regularly during high tides, a phenomenon called sunny day flooding or nuisance flooding, and this is with only the current 1 to 2 feet of sea level rise since pre-industrial times. In a 2-degree world, Miami faces severe challenges. Even moderate sea level rise scenarios, 1 to 2 feet by 2100, would render large portions of the city prone to chronic flooding that makes normal life and economic activity increasingly impractical. Insurance becomes unaffordable or unavailable. Property values in flood-prone areas decline. The tax base erodes. Infrastructure, roads, sewage systems, drinking water supply becomes increasingly difficult and expensive to maintain. Miami's situation illustrates a challenge that many coastal cities face. The economics of adaptation are brutal. Building seawalls, elevating streets and buildings, redesigning drainage systems for the new climate. These are extraordinarily expensive undertakings that provide only temporary protection, given the long-term trajectory of sea level rise. Some economists have argued that for the most vulnerable cities, managed retreat, the systematic, planned relocation of people and infrastructure away from areas that will become uninhabitable, is more cost-effective than defending them. But managed retreat is politically and practically extraordinarily difficult. Mumbai, with a population of over 20 million, is one of the most densely populated coastal cities in the world. It lies on a peninsula surrounded by ocean, with large areas barely above sea level. Mumbai already experiences severe seasonal flooding during the monsoon season, and the 2005 floods that killed over 1,000 people have become a reference point for what more intense rainfall can do to the city's overwhelmed drainage systems. In a 2-degree world, the combination of sea level rise and intensified monsoon precipitation creates a severe challenge for Mumbai. The city's informal settlements, home to roughly half its population, are particularly vulnerable, located in low-lying areas without the infrastructure or resources to adapt. The economic consequences of disruption to Mumbai, India's financial capital, would reverberate across the entire Indian economy. Bangladesh provides perhaps the starkest example of climate vulnerability at national scale. The country is largely a river delta, with much of its territory barely above sea level. It is one of the most densely populated countries in the world. It already experiences devastating cyclones and flooding. In a 2-degree world, sea level rise, increasing cyclone intensity, and changes to the monsoon system combine to make large portions of Bangladesh increasingly difficult to inhabit. The country's own climate scientists and government acknowledge that millions of people may ultimately need to relocate either within Bangladesh or internationally. Then there is the question of water supply in major cities that depend on glaciers or snowmelt. Lima, Peru, a city of 10 million people in one of the world's driest deserts, gets much of its water from Andean glaciers that are rapidly retreating. In a 2-degree world, Lima faces a serious medium-term water supply crisis. Similarly, cities in the western United States that depend on Colorado River water face increasing shortages as the snowpack that feeds the river declines and as growing demand from agriculture and other cities competes for a shrinking resource. Jakarta, Indonesia's capital and home to over 30 million people in its metropolitan area, is already sinking due to groundwater extraction while simultaneously facing rising seas. The Indonesian government made the decision to relocate the national capital to a new city on Borneo, partly in recognition that Jakarta's long-term habitability is uncertain. This unprecedented step, moving a capital city partly due to climate vulnerability, hints at the extraordinary scale of adaptation decisions that 2 degrees of warming will force upon governments worldwide. The economic consequences of 2 degrees of global warming are difficult to comprehend in their full magnitude. Economists have been attempting to model these costs for decades, and their estimates have been consistently revised upward as understanding of the physical impacts has improved and as the limitations of earlier economic models have become apparent. The challenge of costing climate change economically is that it requires putting dollar values on things that don't have obvious market prices. The loss of biodiversity, the cultural and psychological costs of displacement, the value of a stable climate system that maintains the conditions for human civilization. It also requires discounting, determining how to value costs and benefits that occur in the future compared to those that occur today. Different assumptions about how to value the future lead to dramatically different total cost estimates. A 2018 analysis published in Nature estimated that 2 degrees of global warming could reduce global GDP by about 1 to 2% compared to a world without climate change, while limiting warming to 1.5 degrees would save roughly $150 trillion worth of damages over the course of the century. However, other analyses, particularly those that attempt to account for the full range of climate risks, including tail risks and tipping points, arrive at much larger estimates. Nobel Prize-winning economist Joseph Stiglitz and others have argued that conventional economic models systematically underestimate the true costs of climate change by failing to adequately account for catastrophic risks, non-linear impacts, and the possibility of cascading tipping points. When these factors are incorporated, the economic case for aggressive climate action becomes even stronger than mainstream analyses suggest. What can be said with confidence is that the costs are enormous and heavily concentrated in the world's most vulnerable regions. Sub-Saharan Africa, South Asia, and small island states regions that have contributed least to the emissions that caused warming stand to suffer the greatest economic and human losses. This fundamental injustice that those least responsible bear the heaviest burden is one of the central ethical dimensions of the climate crisis. Agriculture, as discussed, faces significant productivity losses across large regions. Coastal infrastructure, ports, roads, buildings, entire neighborhoods faces increasing costs from flooding and storm damage. The energy system requires fundamental transformation, imposing large transition costs while also potentially generating large savings from avoided fossil fuel purchases. Healthcare systems face increasing costs from climate-related illness, heat mortality, and the health consequences of extreme weather events. The insurance industry is already experiencing the economic reality of climate change. Global insured losses from natural disasters, which include a disproportionate share of the most climate-sensitive events like hurricanes, floods, and wildfires, have risen dramatically over recent decades. Reinsurance companies, which insure the insurance companies, are increasingly concerned about their ability to price and absorb climate-related risks. If the insurance industry withdraws from high-risk areas, it removes a critical economic buffering mechanism that allows societies to recover from disasters. There are also the economic costs that come from supply chain disruption. The global economy is deeply interconnected, and climate impacts in one region ripple globally. Agricultural failures in major producing regions drive up food prices worldwide. Infrastructure damage disrupts shipping. Climate-related political instability in key resource-producing regions affects commodity markets. The 2011 Thailand floods, which were not directly climate-driven but illustrated the vulnerability of global supply chains to extreme weather, disrupted global automobile and hard drive production for months due to flooded factories. The economic analysis points in one consistent direction. The costs of acting on climate change are substantially lower than the costs of inaction. But the distribution of those costs, both the costs of action and the costs of inaction, is deeply unequal, and that inequality poses profound challenges for international cooperation. No region on Earth is experiencing the effects of climate change more intensely than the Arctic. The Arctic is warming approximately 4 times faster than the global average, a phenomenon called Arctic amplification, and the changes happening there have consequences that extend far beyond the polar regions. Why does the Arctic warm so much faster? The primary answer involves ice albedo feedback, one of the most powerful amplifying mechanisms in the climate system. Snow and ice are highly reflective. They bounce roughly 80 to 90% of incoming sunlight back into space. When snow and ice melt and expose darker ocean water or land surface, the surface absorbs instead of reflecting most of the incoming sunlight. This absorbed energy warms the surface further, melting more snow and ice, which absorbs more energy, another vicious cycle. The Arctic has already lost approximately 2/3 of its summer sea ice volume since satellite measurements began in the late 1970s. By the late 2030s, the Arctic Ocean will likely experience its first ice-free summer. In a 2-degree world, ice-free Arctic summers become routine, dramatically altering the ecology of the region and opening new shipping routes and resource extraction opportunities, though also raising concerns about geopolitical competition for Arctic resources. The impacts of Arctic change on weather patterns elsewhere are the subject of intense scientific debate. One hypothesis, associated primarily with climate scientist Jennifer Francis, suggests that Arctic warming is destabilizing the polar vortex, the ring of cold air and wind that normally contains polar conditions near the poles, allowing cold Arctic air to spill further south. This could explain the increasing frequency of sudden stratospheric warming events that precede severe winter weather in populated mid-latitude regions, including the events that caused the catastrophic Texas freeze in February 2021. While the connection between Arctic warming and mid-latitude weather remains somewhat contested, the evidence for increasing volatility in mid-latitude weather patterns is consistent with a destabilizing polar vortex. In a 2-degree world, the question is whether this effect intensifies, creating more frequent and severe disruptions to winter weather in heavily populated regions. The thawing of permafrost, already discussed in the context of carbon feedbacks, has additional direct consequences in Arctic and subarctic regions. In Alaska, Canada, and Siberia, towns and cities built on permafrost are experiencing damage to foundations, roads, and infrastructure as the ground thaws and shifts. In Siberia, dramatic permafrost pits, holes opening in the ground where methane is bubbling up through thawing soil, have been discovered and are increasing in frequency. Indigenous communities in the Arctic face perhaps the most immediate and complete disruption of any human population. Communities in Alaska, northern Canada, Greenland, and Siberia have developed cultures, economies, and survival strategies perfectly adapted to Arctic conditions over thousands of years. The rapid transformation of those conditions, sea ice that is thinner and less predictable, migration patterns of the animals they hunt that are shifting, permafrost thaw that undermines homes and infrastructure, is disrupting ways of life that can't simply be relocated or adapted to new conditions. The opening of the Arctic to shipping creates economic opportunities. The Northern Sea route along Russia's Arctic coast is already seeing increased traffic, offering a shorter path between Europe and Asia than the Suez Canal route. But the same opening that creates shipping opportunities also threatens the Arctic ecosystems and raises geopolitical tensions as nations compete for access to Arctic resources, including potentially vast deposits of oil, gas, and minerals that are becoming accessible as sea ice retreats. Throughout this exploration of a 2-degree world, it's worth periodically asking, what would be different at 1.5 degrees? The Paris Agreement's more ambitious goal wasn't chosen randomly. It represents the upper bound of a temperature range that scientists believe preserves significantly more of the world's natural and human systems. The difference between 1.5 and 2 degrees of warming may sound trivial, but in the climate system, where changes are non-linear and thresholds matter enormously, that half-degree makes a profound difference. At 1.5 degrees, some coral reefs survive. Roughly 10 to 30% of coral reefs could persist at 1.5 degrees, compared to essentially 0% at 2 degrees. The survival of even a fraction of the world's coral reefs means the survival of the extraordinary biodiversity they support and the fisheries and coastal protection services they provide to hundreds of millions of people. At 1.5 degrees, the chance of the Greenland ice sheet crossing its critical tipping point is substantially lower. The probability of major disruption to the AMOC is lower. The risk of various regional tipping points being crossed is lower. Across virtually every category of risk, the probability distributions shift meaningfully in the better direction at 1.5 degrees compared to 2 degrees. At 1.5 degrees, approximately 6% of insects, 8% of plants, and 4% of vertebrates would face severe climate change impacts on their ranges bad, but significantly better than the estimates for 2 degrees, which roughly double these numbers. For human systems, the 1.5 versus 2 degree difference is particularly stark in the most vulnerable regions. In sub-Saharan Africa, hundreds of millions more people face water scarcity at 2 degrees compared to 1.5 degrees. In South Asia, exposure to extreme heat events increases substantially between the two thresholds. For small island states, the difference in sea level rise between 1.5 and 2 degrees, roughly 4 inches, can be the difference between marginally habitable and effectively uninhabitable. The IPCC's 2018 Special Report on Global Warming of 1.5 degrees documented these differences in detail and concluded that the difference between 1.5 and 2 degrees was significant and meaningful. Across virtually every impact category, the report also noted that limiting warming to 1.5 degrees would require rapid, far-reaching, and unprecedented changes in all aspects of society changes, in energy, land use, urban planning, and industry, that the report characterized as having no documented historical precedent in terms of speed and scale. We are currently on track for somewhere between 2.5 and 3 degrees of warming by the end of this century under current policies. Even the most optimistic scenarios, consistent with current commitments, suggest 2 degrees is now very difficult to avoid. The 1.5 degree target remains theoretically achievable but requires a dramatic acceleration of emissions reductions beyond what is currently planned. This isn't a counsel of despair. Every fraction of a degree matters. Every ton of emissions matters. Every year of earlier action makes a difference. But it is a sober recognition of where we stand and what would be required to change the trajectory meaningfully. Throughout history, humanity has demonstrated remarkable adaptability. We live in the Arctic and in the Sahara, at sea level and at altitude, in rainforests and in deserts. This adaptability will be called upon as the climate changes, and understanding what adaptation looks like, what it can achieve, and where its limits lie is essential to a complete picture of a 2-degree world. Adaptation to climate change encompasses an enormous range of actions, from infrastructure investments to agricultural innovation, from managed retreat of coastal communities to urban greening programs that reduce heat island effects. Some adaptation is already underway, driven by current climate impact. More will be required as impacts intensify. In agriculture, adaptation includes developing heat-tolerant and drought-resistant crop varieties, shifting planting dates to account for changed growing seasons, improving water use efficiency through precision irrigation, and diversifying crop rotations to reduce vulnerability to any single crop failure. Plant breeding programs are already working on crops adapted to warmer, drier conditions. The application of genomics and artificial intelligence to crop development has accelerated the pace of innovation. But there are fundamental biological limits to how much crops can adapt to extreme heat and water stress. Water management adaptation includes building more water storage capacity to capture the more intense but shorter precipitation events of a warmer world, improving irrigation efficiency, and managing groundwater more sustainably. In some regions, desalination converting seawater to freshwater will play a larger role as traditional freshwater sources decline. In others, large-scale water transfer projects will redirect water from areas of relative surplus to areas of deficit. Coastal adaptation involves a spectrum of responses. Hard infrastructure seawalls, levees, surge barriers can protect specific areas from flooding and storm surge. Rotterdam in the Netherlands is often held up as a model for sophisticated coastal flood management, with a system of barriers, pumps, and water squares that manage the risks of a city that is partly below sea level. But Dutch-style flood management is extraordinarily expensive and requires strong institutional capacity, factors not present in many of the most vulnerable coastal cities. Nature-based coastal protection restoring mangroves, seagrasses, and coral reefs that buffer coasts from wave energy is increasingly recognized as both effective and cost-efficient. Healthy coastal ecosystems can absorb storm energy, trap sediment, and build elevation over time. But in a 2-degree world, many of these coastal ecosystems face their own climate stresses. In human health, adaptation includes strengthening heat early warning systems and response protocols, expanding shade and cooling infrastructure in vulnerable urban areas, and disease surveillance and control systems for expanding vector-borne diseases. Air conditioning provides direct protection from heat stress, but contributes to warming through its energy consumption and refrigerant emissions, a feedback that represents an important adaptation mitigation tension. Urban adaptation is one of the most promising areas because cities represent concentrated populations and economic activity where well-designed changes can have large-scale impacts. Urban forests, planting trees throughout city fabric, reduce temperatures through evapotranspiration and shading. Green roofs and walls insulate buildings and reduce runoff. Permeable pavement allows water to filter into the ground rather than running off in floods. Building codes that require better insulation and passive cooling reduce the energy demand for air conditioning while improving resilience. But adaptation has limits. Some impacts simply cannot be adapted to. A permanent 1-foot rise in sea level is adaptable in many locations with enough investment. A 3-foot rise combined with more intense storms, begins to overwhelm the costs and possibilities of adaptation for many low-lying areas. Some regions will face combinations of heat, humidity, drought, flooding, and storm risk that make continued habitation economically or physically impossible, regardless of adaptation investment. The justice dimensions of adaptation cannot be ignored. The communities with the greatest resources can adapt to climate change better than those with fewer resources. Wealthy nations can afford seawalls, heat-resistant infrastructure, and agricultural innovation. Poor nations, small island states, and marginalized communities within all nations face the same or worse physical impacts with far fewer resources to respond. This inequality in adaptive capacity means that even if wealthy nations successfully adapt to 2 degrees of warming, the human cost of that temperature target will fall disproportionately on those least able to protect themselves. No discussion of climate change and its consequences is complete without addressing the technological dimension. What role can technology play in preventing 2 degrees of warming, or in adapting to it, or even through radical approaches like geoengineering in reversing it? On the prevention side, the clean energy transition is the most fundamental technological development, with the potential to prevent the worst climate outcomes. The costs of solar photovoltaic power and wind energy have fallen by more than 90% over the past decade, making them the cheapest sources of new electricity generation in most of the world. Battery storage technology is improving rapidly, addressing one of the key challenges of intermittent renewable energy. Electric vehicles are approaching cost parity with internal combustion vehicles in many markets. This technological progress is real and significant, but technology deployment is not just a matter of invention. It requires financing, infrastructure, policy support, supply chains, skilled workers, and overcoming the institutional inertia of established energy systems. The pace of the clean energy transition, while accelerating, remains slower than the pace required to limit warming to 1.5 or even 2 degrees. Carbon capture and storage technologies that capture carbon dioxide from the atmosphere or from industrial exhaust and store it underground may play a role in addressing the stock of carbon already accumulated in the atmosphere. Direct air capture machines that remove carbon dioxide from ambient air exist and are operating at commercial scale, though current costs remain high and the scale needed to significantly affect atmospheric concentrations is enormous. The most speculative but potentially high-impact technological frontier is geoengineering deliberate large-scale interventions in Earth's climate system to offset warming. The most widely discussed approach is stratospheric aerosol injection, releasing reflective particles into the stratosphere to reflect a small fraction of incoming sunlight, cooling the planet. This approach is inspired by the natural effect of large volcanic eruptions, which have historically caused short-term global cooling when they inject sulfur dioxide into the stratosphere. Research suggests that stratospheric aerosol injection could, in principle, reduce global average temperatures significantly at relatively low direct cost. But it comes with severe risks and uncertainties. It would alter precipitation patterns, potentially causing droughts in some regions while providing cooling elsewhere. It would do nothing to address ocean acidification. It would require continuous maintenance. If injections stopped suddenly after decades of implementation, temperatures would rebound rapidly, a scenario called termination shock, potentially causing faster warming than if geoengineering had never been used. Most importantly, stratospheric aerosol injection raises profound governance questions. If one nation or group of nations began unilaterally altering the global climate through geoengineering, how would others respond? Who has the right to decide what climate conditions the entire world experiences? The geopolitical risks are severe. A more benign geoengineering approach involves enhancing the ocean's capacity to absorb carbon through ion fertilization or other means. But the ecological risks are poorly understood, and the effectiveness and permanence of carbon storage are uncertain. The technology picture for climate change is complex. There is real and important progress in clean energy that provides genuine hope for reducing future emissions. There are promising but still expensive carbon removal technologies that could help address the carbon stock problem. And there are highly uncertain and risky geoengineering approaches that some see as last resort options and others see as dangerous distractions from emissions reductions. No single technology will solve the climate problem, but the combination of rapid clean energy deployment, energy efficiency improvement, land use changes, and potentially carbon removal could, if implemented at sufficient scale and speed, still significantly limit how far beyond 2 degrees the world warms. We have traveled through ice sheets and ocean chemistry, through permafrost and polar vortices, through flooded cities and collapsing ecosystems, through economics and engineering and ethics. We've seen what a 2-degree world looks like across virtually every dimension of planetary and human systems. Now, standing at the end of this journey, let's ask the question that underlies all of it. What kind of world are we in the process of leaving to the generations that will come after us? The children born today will live most of their lives in a world shaped by whether we do or do not cross 2 degrees of warming. They will experience the climate of mid-century and beyond, a climate whose character is being determined now by decisions being made about energy systems, land use, and economic organization. Those children have no vote in these decisions. They have no seat at the table where the policies are being debated, and yet they will bear the consequences more fully than any living generation. 2 degrees of warming, if achieved, represents a world that is substantially damaged relative to the Holocene world in which human civilization developed. Coral reefs largely gone, Arctic sea ice gone in summer, significant portions of the world's glaciers retreated or gone, sea levels rising and continuing to rise for centuries, weather patterns disrupted, ecosystems disrupted, and hundreds of thousands of species extinct or severely threatened. Hundreds of millions of people displaced or facing severe climate stress. But 2 degrees is also better than 3 degrees, and 3 degrees is better than 4 degrees, and every fraction of a degree matters, for every category of impact, across every region, for every generation. This is perhaps the most important thing to hold on to as we contemplate what 2 degrees means. The story isn't over. The 2-degree world is not inevitable. The trajectory of warming is determined by human choices about energy, about land use, about economics, about what we value and how we govern our collective behavior. Those choices are being made now, every year, in legislatures and boardrooms, and individual decisions about how to live and what to support. The physics of climate change doesn't offer easy answers. The inertia of the climate system means that some warming and some impacts are already committed, regardless of what we do. The carbon dioxide already in the atmosphere will warm the planet for decades and centuries. Some of the changes we've described in this journey are already underway and will continue. But the difference between the plausible better outcomes and the plausible worse outcomes, the difference between 2 degrees and 3 or 4 is enormous. It is the difference between a severely stressed but still largely functional biosphere and an ecosystem's in widespread collapse. It is the difference between manageable, if enormously costly, human adaptation challenges and civilization-scale disruptions that could destabilize societies worldwide. The temperature of the Earth in 2100 and beyond is not fixed. It depends on what happens in the next decade, not just the next century. The carbon budget, the total amount of carbon dioxide we can emit, while still having a reasonable chance of limiting warming to 2 degrees, is limited, but not yet exhausted. Every year of reduced emissions preserves more of that budget. Every year of delay exhausts more of it. The science of climate change has never been more certain. The understanding of impacts has never been more detailed. The technologies needed for the energy transition have never been more available or more affordable. And the cost of inaction has never been more apparent in real-world observations of already occurring impacts. 2 degrees. The number that began this journey as an abstraction, almost dismissibly small, has revealed itself as the threshold between the world we know and a world of profound and largely irreversible change. We've seen the ice sheets begin their slow-motion march toward the ocean. We've watched the coral reefs bleach and die under warming waters. We've felt the intensifying heat waves, the more powerful storms, the floods that refuse to recede and the droughts that refuse to end. We've followed the cascading ecosystems as species shift, struggle, and disappear. We've stood in the flooded streets of coastal cities and in the drought-cracked fields where crops once grew. We've grappled with the tipping points that could put the climate system beyond human influence entirely. And we've seen the human dimension. The hundreds of millions displaced, the food systems stressed, the health systems strained, the economies disrupted by costs that dwarf the price of prevention. We've seen which communities and which nations bear the heaviest burden, invariably the ones least responsible for the problem. But we've also seen the possibility of a different path. The technology that can replace fossil fuels already exists and is already cheaper than the alternatives in much of the world. The capacity to adapt is real, if not unlimited. The understanding of what needs to be done is clear, even if the political will to do it has been inconsistent. The 2-degree world is not a fate to be passively accepted. It is a challenge to be actively engaged with every tool that science, technology, policy, and human ingenuity can bring to bear. The planet has been warming for 2.5 centuries since the Industrial Revolution began. The consequences are already being felt. The trajectory is worrying. But the story of Earth's climate in the 21st century, the story of whether we cross 2 degrees, how far beyond we go, and how much we preserve for the generations that follow is still being written. Every power plant that switches from coal to solar, every forest that is protected instead of cut, every policy that puts a price on carbon, every building that is designed for efficiency rather than waste, every conversation that moves from denial or despair to problem-solving engagement. These are the sentences in the story we're still writing. 2 degrees is a number. But the world it represents, the world of our children and grandchildren, is not a number. It is a living reality, teeming with the remnants of ecosystems that once covered the earth, shaped by the choices made by the generation that knew what was coming and had to decide what to do about it. That generation is us. That decision is now. Earth can still be a world worth inheriting. but only if we act as if that matters, because it does, more than any other question our civilization currently faces. The temperature is rising. The question is how high we let it go.